All right, thank you, Mamata. A lot of people, these aspect slope maps are getting pretty popular in cartography lately. They're interesting because they sort of tell you everything you need to know about the shape of the terrain, and they kind of avoid some of the ambiguities in shaded reliefs that we've been talking about in some of the presentations earlier in the conference. They do this by using two polar coordinates to show orientation, the aspect and the slope. There is a Cartesian version of this raster that I'm going to be talking about today, and that's what a normal map is. So how do these work? So say you have a terrain. It's made up of a bunch of faces. On each of those faces, you can draw a three-dimensional vector that is perpendicular to the face and has a length of exactly 1 unit. That is the normal. Because it's a 3D vector, you can break it up into its x, y, and z coordinates, its x, y, and z components. Each of those, because the normal itself has a length of 1, each of those components will have a value somewhere between -1 and 1, which makes it really easy to map it to any sort of RGB raster. In the case of a 24-bit RGB raster, you just turn -1 into 0, 1 into 255, and then all the values in between, you just interpolate between those endpoints. So in this particular case, those XYZ components become an RGB value of 194.179.224, which is that lavender color I've put on this polygon here. If you do that for every cell in an elevation raster, you've got a normal map. So they have some interesting properties. If you break it back up into its component channels, it looks kind of like 3 sets of shaded reliefs, one lit from the east, one lit from the north, one lit from directly above. You can kind of also think of these as rasters that represent how much the surface is facing in any of these directions. Also notice that the blue band is much brighter than the others because on a top-down map, you're never going to see a face that is facing downward. So that z component is always going to have a value of at least 0. Another interesting property of these normal maps is that if you compare them to aspect maps have a range of values between, they go from 0 to 360 degrees, and then they roll over back to 0. Well, just like if you're trying to show a polygon that's crossing the international date line, this can sometimes lead to issues if you're trying to perform certain kinds of analyses on these. If you look at this normal map here that is just the x and y components, though, there is no such discontinuity. Now, I came into GIS and cartography through computer graphics, where normal maps have been in use for some time. And so I knew about normal maps before I learned of aspect maps. And I thought it was kind of weird that given the discontinuity in aspect maps and the lack of one in normal maps, that the aspect maps were seen a lot more in GIS than normal maps are. So for the last few years, I've been experimenting with ways to use normal maps in GIS and cartography. And I'm going to share one of my favorites with you today. Pyramid Shader is a utility that Bernard Yenny, myself, and Jim Maynard, and a bunch of others at our cartography and geovisualization group have created. It's been talked about a lot so far in this conference. The way that works is you take a DEM and you run a set of Gaussian filters on it. So they're different sizes. The first one is a radius of 1 pixel, then 2, 4, 8, 16, doubles every time. You take the difference between each successive set of those Gaussian filters, And what that gives you in the bottom row there is the contribution that each scale of detail makes to the original DEM. If you sum all those back together, you get the original DEM, which means that you can do a weighted sum. So you can say that the finer scales of detail make less of an impact than larger scales. And this lets you get past that problem that Tom talked about on Wednesday, where you can take out the noise and the gray smudges on small scale maps, but you haven't actually gotten rid of that small scale detail. It's still there, it's just not as prominent. So I've been looking at how to incorporate normal maps into this, and it turns out that there's actually more you can do with them with this scheme. Part of it is that a normal map is actually the intermediate step between an elevation map and a hill shade. Because the most common hill shading algorithms, all they do is they take a look at the difference between the incoming light vector and the surface normal. So anytime you make a hill shade, you're already going through the process of making a normal map. It's just hidden from you. The other interesting thing is that once you're using a normal map, you're no longer working with elevations, you're working with orientations. Each of these colors is a separate orientation, and the farther apart those colors are, the more different those orientations are. This is really good if you're trying to do terrain generalization, because we want to keep those sharp differences in surface orientation, which are the ridges, the valleys, any creases in terrain. But we do want to minimize any small differences in orientation. This is on a normal map, you can do something that you can't with a DEM if this is your goal, which is to use median filters and high pass filters on the normal map to smooth out those small changes in orientation, but keep the major differences. And I've done that here on this normal map, so you can see I still have those sharp ridges, even though the details on any given face have been smoothed out. So if I do this for several different scales, just like we do in Pyramid Shader, and then take their differences and sum them back together, we get a shaded relief that looks like this. We can compare that to the conventional hill shading algorithm. I can also make another comparison between Edward Imhoff's hand-drawn relief and normal pyramid shading with some slightly different settings. So I have automated this process and am building it into a Python toolbox for ArcGIS Pro that I hope to be releasing in the next few months. Most of the development work on it is already done. I mostly just need to test and document it. It's in there along with a bunch of other tools. Some of them use normal maps, and some of them are just simple things like a Gaussian filter and a high-pass filter that are easy to change the radius of. Another tool that I added in there that I've been working on a lot recently, I don't have time, unfortunately, to go into as much detail about it, is ambient occlusion. If you're doing hill shading, you're mostly concerned with direct lighting from, say, the sun. But there is also indirect lighting from the sky, which sort of acts as this hemispherical light source surrounding your entire scene. If you have any sort of deep canyons or highly concave surfaces, their view of the sky is occluded and therefore darker. But also you can see that the orientation of the surface comes into play as well, because that floor down there in that cavity has a direct view of the sky, while the walls towards the base are looking just at the walls directly across from them. They're not directly looking at the sky, so they appear darker. Again, I don't have time to go into detail on it, but it turns out that despite the fact that this is very slow to calculate in a lot of algorithms because you have to sample how much of the sky a point can see, This is a curvature problem, which means you can use normal maps and this, this pyramid scaling technique to get this much faster, and it's basically just combining a whole bunch of rasters together. And because I've used the pyramids to make it sensitive to different scales, or I can choose to make it sensitive to different scales, it allows me to do some interesting things here. Like I can make one pass where the ambient occlusion is only sensitive to very large features, which is giving you that broad darkening of the glacial valleys in this hillshade. And then I can do another one where it's only sensitive to very small features that are only a few pixels wide, which is what you see in those small gullies there. And so I have this sort of bimodal distribution that gives me a lot more control, and if I'm trying to recreate a more hand-drawn look, it's a lot more useful than that than just trying to do it with maybe a more physically accurate technique, in some cases. I can give another example. Here is a conventional analytical relief of Mount Hood in Oregon. Here is Mount Hood with the normal pyramid shading, and then with the ambient occlusion layered on top of that. All right, so at that point, if I have left time for it, I think we can go to questions. Yep.
Could you say again what a normal map is?
The question was, what is a normal map? It is basically an RGB raster that represents the X, Y, and Z components of the surface normal at a point on a point on a surface. So basically, you have this this 3D vector here that's perpendicular to the surface, and I break it down into its X, Y, and Z components because it's a 3D vector, and then I portray the magnitude of each of those components with a band of an RGB raster. Welcome. Yes?
What's your plan for the occlusion algorithm? Are you releasing that as well as part of one of your toolkits?
Yeah, it's a Python It's a Python toolbox, so when I release it, the source code will be readable to anybody who downloads it. Our plan is to release it with a license that will allow other people to implement it in whatever platform they want. Bernie has already asked if I'm willing to add it to Pyramid Shader, but I don't think I have the time. Yeah.
Any other questions? Okay, thank you.
Thank you.